All right, buckle up for a deep dive. Today, we're cutting through the complexity of something that, well, it quietly affects us all, how we age.
Hmm.
And specifically, the chronic diseases that often come along with it. We're really zeroing in on fibrosis today.
Yeah, that the sort of sneaky culprit in health decline.
Exactly. And we're uncovering two pretty incredible advancements, new biomarkers giving us early warnings, and how AI is actually designing completely new treatments now.
It's fascinating stuff.
Our goal here, give you a fast track to understanding some really cutting-edge medical breakthroughs happening right now.
And it's such a critical area. Fibrosis, I mean, at its core, it's this pathological accumulation of proteins.
Right. Proteins building up where they shouldn't.
Exactly. And that leads to tissue stiffening, organs not working properly.
Yeah.
It's central to really tough diseases like idiopathic pulmonary fibrosis, IPF.
And you mentioned aging itself.
Yes, remarkably, it seems to be a core component of the aging process too. So understanding this is, well, it's key if we want to extend our healthy years, you know?
Okay, so if fibrosis is this, like, quiet, insidious threat, how do we even start to spot it early? Our deep dive kept pointing to periostin and TIMP1.
Ah, yes, those two.
For those of us tracking aging research, these names, these biomarkers, they've been generating a fair bit of buzz. What exactly are they? Why so crucial all of a sudden?
Well, what's really remarkable about periostin and TIMP1 is they're not just some obscure lab values anymore. They're measurable indicators of fibrotic activity.
Okay.
And we're increasingly recognizing their strong association with systemic inflammation, ongoing tissue remodeling, even physical decline.
So like real world impact.
Definitely. We're seeing clear correlations with things like frailty, poor mobility, just lower physical well-being overall in older adults. These biomarkers, they potentially offer a window into the sort of biological age of our tissues, giving us a much earlier heads up than we've ever had.
So like an early warning system. That sounds incredibly powerful.
It is.
But, you know, detection is one thing, treatment's another. You mentioned our sources highlight some limitations. What's holding back direct therapies targeting these markers? And what's the next big thing for treatment?
That's the key question. While periostin and TIMP1 are valuable as, let's say, diagnostic markers, directly targeting them with therapies, that's still very, very early stage.
That's early.
Well, for instance, therapies targeting periostin haven't even reached human testing yet. And TIMP1 inhibition, that's still being explored in preclinical animal models.
Ah, so not in humans yet.
Not yet. That's a significant hurdle to cross before we see treatments based on them.
Okay, so we've got these early warnings developing, but what about actual treatments? This is where our deep dive uncovered something that sounds truly revolutionary, a drug called Rentosertib.
Yes, Rentosertib.
And what makes it so groundbreaking isn't just what it does, but how it was discovered, right?
Exactly. This is genuinely a milestone.
Oh.
Rentosertib is the first AI-designed small molecule inhibitor.
Okay, break that down. Small molecule.
Think of a small molecule as like a tiny, precisely engineered key. It's designed to block a very specific biological pathway.
Got it.
In this case, it targets something called TNIK. It's a protein we now know plays a crucial role in the whole fibrotic process.
And this was developed by in silico medicine.
That's right. And Rentosertib just completed a phase 2A clinical trial for idiopathic pulmonary fibrosis. The results were remarkably promising.
How promising?
Patients getting the 60 milligram dose showed a 98.4 millimol increase in their forced vital capacity. That's FVC, a key measure of lung function.
Wow, compared to
A decline of 20.3 millimol in the placebo group. And crucially, this all came with a favorable safety profile.
a 98.4 millimol increase in lung capacity. Right. For someone with IPF, that's not just a number, that's huge, right? That's breathing better, living better.
Is potentially life-changing, a significant improvement.
So this isn't just like a slightly better drug, then it feels like a completely different way of finding drugs. What's the real aha moment here for medicine?
Exactly right. The aha is that AI isn't just, assisting researchers. It's generating the breakthroughs.
Generating them.
Yes. This isn't just a novel compound. It's hitting a novel mechanism. And it was designed and optimized entirely using AI tools. Right from finding the target, TNIK, all the way to generating the molecule itself. We're talking about a potential paradigm shift, something that could radically accelerate what used to take, decades of trial and error in labs. That's the real leap for precision medicine.
An AI-designed drug. It sounds like a genuine revolution brewing. But, like with any big breakthrough, there are always new questions, aren't there?
Always.
What are the key challenges still ahead? As we look towards the future of these AI-driven therapies and maybe those biomarker-guided treatments too?
Well, there's definitely more research needed. For the biomarkers, we need to figure out if we can target them therapeutically without messing up natural tissue repair processes. That's important.
Right, don't want to cause new problems.
Precisely. And for AI-designed drugs like Rentosertib, long-term safety and efficacy data are absolutely essential. We only have phase 2A results so far.
Makes sense. Need to see how it holds up over time.
But if we connect this to the bigger picture, we really do seem to be entering a new era. The fusion of AI with molecular biology, it might just radically change how we understand, detect, and ultimately treat fibrosis.
So what's next on the horizon?
Well, phase 3 trials for Rentosertib are planned, which is the next big step. And there's growing interest generally in biomarker-guided therapy. The next decade could bring truly transformative treatments.
Not just for IPF.
Not just for IPF, but potentially for age-related fibrotic conditions across multiple organs. Think liver, kidney, heart.
What an exciting prospect. This intersection of cellular biomarkers and AI-driven drug development, it's offering a powerful new pathway, isn't it?
It really is. A pathway to tackle fibrosis, one of the most insidious contributors to chronic disease and aging.
And as this translational research keeps bridging that gap, between the molecular insight and the clinical application, a future of personalized, effective antifibrotic therapy, it seems increasingly within reach.
It does feel that way.
So a final thought for you listening. What new possibilities does this open up for your own health journey? And how might this shift your perspective on the future of medicine itself?